So guys, what is the point of this chapter? End of it, the point of studying thermodynamics is to relate to real world systems like, say, a piston or an engine, study of an engine, understand engine. End of it, maybe build as well. I would like to. That's one thing in my bucket list, to build an engine, to build a car. Something that moves at least. Maybe not an actual car, but go-kart maybe. Okay, so this is my agenda. So basically, I should be able to talk about the pressure, volume and temperature of a given system at any point of time. But honestly, to begin with, say we are at 0, is it not? We are just starting off. To begin with, these are very fast. I mean, they literally are very fast, right? So they are very fast. So what do we do? What is the obvious thing to do if we have a system which is very fast, but we want to understand it? Like if someone is talking to us and we want to understand them and they are talking very fast and the subject is new to us, what do? We ask them to slow it down. You guys agree? So when we slow things down in thermodynamics, it has a special name, and that is quasi-static. Quasi, the word quasi means almost, and static, you guys understand? Static, stationary. So almost stationary, not exactly stationary, but almost stationary. And that is your quasi-static process in thermodynamics. So basic idea over here is the process is infinitely slow. Quasi-static process is infinitely slow such that the system has no sudden jump in temperature, pressure and volume. That's the basic idea. So here is a good picture to depict that. So we have a piston getting pushed down by sand. So basically we are just dropping every second a bit of sand so that the piston goes slowly down. And if you want the piston to come up, we remove grain by grain, if it's possible. We remove grain by grain and study the system. This is just an ideal case, and this is just it's not even a proper piston, but point is, this shows a good, it helps us relate to what we are trying to do. It's a good picture. So pressure, volume and temperature can change, but they remain well defined and uniform at each instance in time. So we know what is happening exactly. Basically, we're telling that. So as a result, the system evolves smoothly and slowly enough that it passes through a continuous sequence of well-defined equilibrium state. So this theoretically we understand it and we are able to draw this. So what we're looking at is a pressure, volume of an ideal gas, and the solid line over here is your related to quasi-static, and the dotted ones over here is your real one. So I just want to take up T1, low temperature. Can you see that the real one is almost same as the quasi-static? Or actually I should be telling the other way around. The quasi-static is quite near to the real one. So it does help us. It does help. So the system evolves smoothly. As you can see, we have a definite handle over what is happening with the pressure and volume for this particular temperature. So this is because of quasi-static. It being quasi-static, it giving us a chance to study it. As simple as that. So as a definition, the system remains infinitely close to thermodynamic equilibrium at every instant. So if someone asks you to define quasi-static, this is how you should define. The quasi-static process, in a quasi-static process, the system remains infinitely close to thermodynamic equilibrium at every instant. So basically, if we talk about a point over here and the neighboring point, let me go to the actual graph. So if I take up a point over here, the immediate surrounding points, right? The pressure and volume, they are predictable. They're very close by. Of course, if I take this point and this point, the values are not close by, that I agree. But if I take the nearby points, they're quite close by, and yeah, the difference is not that big. That's the point. So it looks like it is almost in equilibrium in the nearby if I just take the nearby points. There's no significant pressure or temperature gradient inside the system. There's no sudden change in the pressure, volume and temperature in quasi-static process. And the pressure, volume, temperature are well defined, uniform and changes continuously. There's no sudden jump. But of course, real life is not that. Real life is more sudden. But yeah, quasi-static process helps us to reach there. So mathematically, what do? We define work to be, say, end of it, everything has to do with work and energy. That's the whole point. So we need to define work for quasi-static also. So delta W is equal to P into delta V. And the total work will be changing, adding up all the changes. And so basically we have to use integration. So there are specific cases like quasi-static plus constant pressure, you end up with this formula. So let me explain that. See, basically if I have to study work, force into displacement. It's the most fundamental formula that we know. Now, small work over here is pressure times of small change in volume. Right? So again, we can derive this formula from the above. So this is valid. If I want to study this entire process from the point wherein we have V1, right, somewhere over here, Vi, and to move to Vf. What do we do to figure out the total work? We integrate this process. We add up basically. So work will be equal to integration of all of this. Again, even this equation will be studied in detail. So we'll analyze this. It might be obvious now, but still we'll understand it better. Okay, so that's the point of quasi-static. So again, real life processes are very fast and not easy to get started with. We can study them, but it's not practical. At least not practical for us to get started with. We need a very simple Siddha Sada process which helps us understand it to begin with. And that process is your quasi-static process. It's a process wherein things are the pressure, volume and temperature. When I tell things, these values are well defined. They're quite practical, very close by. And with that as our basis, we move on to understand the real one. Okay. So yeah, you can pause, have a look.